This is the journal club presentation on the foundation model for cardiac time series via masked latent attention. The theme of this presentation is the automated cardiovascular disease diagnosis using ECG data, electrocardiogram. This is the recording of the heart's electrical activity, and it is the dominant major modality for such clinical diagnosis because it is cost-effective and non-invasive, and it has been used for many years. So now it has a mature clinical interpretation pipeline. The standard ECG has 12 leads, including 6 in the limbs and 6 precordial leads. And these leads, it's important to note that they're not independent. There are correlations between the 12 leads because these share autonomy and semantics information. And this will be the key of ECG diagnosis, whether it's human diagnosis or automated machine learning methods diagnosis. So there are several current automated diagnosis methods, including the early ones that did end-to-end learning from raw ECG data with CNNs or recurrent models. More recently, the state-of-the-art solutions are using foundation models to learn from raw ECGs. And the reason for that is that foundation models can reduce the dependence of rare and expensive medical labels, and it enables transfer across tasks and different cohorts. However, these existing solutions are not as good as human diagnosis yet because they are missing an important point, which is the cross-lead correspondence, which means the shared information among different ECG leads. As I mentioned earlier, there are correlations between them. They're not independent, but most of these existing state-of-the-art methods treats them as independent input channels. There is a solution which tried to address such issue by employing the multi-lead MAE, which stands for masked autoencoder reconstruction with lead alignment. It is effective, but the design is rather complicated, and it's still underutilized the higher order relationship among leads. So the gaps to fill for this domain is to develop a model to learn cross-lead relationship in a simpler design. The proposed work, latent attention mask autoencoder foundation model, is trying to fill these gaps. The latent attention module, which is the multi-head, multi-layer self-attention block with the CLS token, which is the similar token used in vision transformer, learns the cross-lead connection and model higher-order interactions. And this module only needs relatively weak supervised settings to provide instance weight summaries, global summaries of all the extracted information. And this foundation model is actually an extension of the masked autoencoder foundation model, which is good at reconstructing missing content from sparse contexts and encourage robust learning. It also uses self-supervised learning, which has a less demand for ground truth or labels, and it is also scalable. So we know what are the major modules in this proposed foundation model and why they're chosen. Now let's take a look at the model architecture and how it actually fills the gap we mentioned in the last page. So taking a look at the graph here, this represents the model architecture. We can see encoders denoted E here and decoders denoted as D here. And in the middle, it is the latent attention transformer or latent attention module. So for the pre-training process, the ECG data, raw data, goes in here, and it applies the mask to mask the ECG data, and then encode each lead, each mask signal separately. And after that, it goes into the latent attention transformer, which produces the CLS tokens denoted by C's here, here, and here. And the CS tokens are basically the global representation of extracted information. And the last step of the pre-training process will be decoding each ECG recording separately. To learn more about the details, let's take a look at the objective function. So the function is comparing the difference between the ECG input data here and the decoded data, denoted as X hat, where X hat is the decoded tokens after going through the latent attention module. And the ZVis here is the visible token masked before the encoders, which is this part. The fine here is the weight of the decoder, which is the same weight applied on the encoder per lead, which means for this lead, their weights, encoder weights and decoder weights are shared, but they're different for the next lead, but they're shared in the same lead. Besides, the most important part of the model is the CLS tokens because it captures the global representation of extracted information from each lead, and it is used in downstream tasks to do predictions. On the right side of this graph, we have a graphical representation of the downstream task or inference. So the predictions are based on the CLS tokens here, and for inference, we don't need to mask our signal, and we also don't need to decode the signal as well. Just input the unseen data, and then it will generate CLS tokens after the latent attention module, and it will lead to the prediction. Now, it is time to test and evaluate the model performance. The developer of this model used this Mimic for ECG dataset. Especially, they used the extended subset, which has raw 12-lead ECG waveforms from the Mimic for ECG datasets paired with ICD-10 labels, which are the codes, the labels for different kinds of cardiovascular diseases. 2 experiments were conducted to evaluate the model performance. The first one is the multi-ICD-10 label prediction. The LAMAE foundation model achieves the area under the RC curve of 0.85 after fine-tuning and 0.834 after linear probing. It has the best performance in predicting ECG salient phenotypes like conduction and rhythm disorders and acute myocardial infarction subtypes, having the AURC of 0.9 or above. However, it has a relatively weaker performance in broader vascular or cerebral vascular diseases. It only achieved an AURC of around 0.7. This result reflects the weaker direct ECG imprint or higher context or label heterogeneity. We can also take a look at the comparison with baseline models. In the following table, it compares the performance between the LAMAE foundation model and the baseline models. And the best result for each ICD code is in bold, and we can see that the LAMAE foundation model beats the baseline models in most of the cardiovascular diseases in this table, although it's only an extracted table, part of the table, but in general, the LAMAE performance outperformed the baseline models. The second experiment is the scaling experiment. This investigated the effect of training sample size, pre-training sample size, on the AURC. And from these 2 graphs, we can see that not only the LAMAE model outperforms other baseline models, it outperforms the stretch train and center baseline models at small pre-training set size. What I mean is the number of training samples less or equal to 5,000. If we take a look at this fine-tuning graph here, we can notice that at 5,000 number of training samples, the AURC of LAMAE is close to 0.7 already. But for other baseline models, they're all below 0.6. And this gap start to strings after 5,000 samples. So this result means that the LAMAE foundation model can achieve better performance using smaller or fewer training samples. In summary, the proposed LAMAE foundation model is a multi-lead masked autoencoder foundation model, which learns the cross-lead structure instead of treating those leads as independent input channels. And it has a simpler design compared to similar state-of-the-art solutions, which also captured the information across leads. And it has promising results. It outperforms the baseline models for most cardiovascular diseases, and it outperforms them at small pre-training data size. So it highlights the efficiency despite the lack of data or labels, and self-supervised learning lower the needs for expensive medical labels. So it works better for most disease, and it works better at small training size. Sounds good, sounds perfect, right? Is this perfect? Not quite. Close enough. But it still has some limitation, so some future work might be required. So as mentioned earlier, some diseases, like the broader vascular diseases, they are difficult to diagnose using only ECG. And in addition, the good results are not exceptionally better than the baseline models. If we take a look at the captures here, we can see that LAMAE achieves 0.8317, the area under the RC curves, but for the baseline models, the highest is 0.8259. It's better, but just by a margin. So these results implies that the ECG single modality methods may reach its bottleneck already. In my opinion, the next step for this project or similar models, the development of these models, could use multiple modalities to provide a more comprehensive analysis or reflection of the actual disease. I think the LAMAE foundation model can be applied to other modalities to capture the cross-modal information. For example, for heart diseases, MRI images and chest X-rays are also common modalities. So we might use the latent attention module to capture the relationship between ECG recordings and the images, as well as we can also use the clinical text or the EHR, electronic health records, as soft training labels or the data itself. So yeah, in summary, this is a successful development of extended foundation models, but here are some potential future work. That's the end of my presentation. Thank you.